Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be calculating again the pH of a buffer solution, but this time I'm going to do it in two ways. I'm going to do it using the equilibrium strategy, but also then I'm going to do it using the Henderson-Hasselbach equation to compare the two. Alright, so first I'm going to do the equilibrium strategy. And that strategy is where you use your balanced equation and your ice chart to figure out what the equilibrium expressions are, and you plug that into your Ka value expression as well. Okay, so we're going to have our ice chart here. So the initial concentrations that we're given is 0.05 molar benzoic acid. So that we're going to put 0.050 here. And then we have 0.150 molar of the anion. So that's going to be 0.150 molar here. And this is essentially 0 at this point in the beginning. So that's what we're starting with. So now we're going to do the change. So we're going to lose a certain amount here. And because this is a 1:1:1 ratio, excuse me, we're going to lose a certain amount of x here. We're going to pick up that same amount here. So plus x, and we have plus x. And then we add these two rows together, and that's going to give us the equilibrium. So 0.050 minus x here. We have plus x here. And we have 0.150 plus x here. And so this is our equilibrium expressions for the concentrations at equilibrium. And so now we can use our Ka value. So Ka is equal to 6.5 times 10 to the negative 5. And that's going to be equal to these two concentrations. So the concentration of H3O plus multiplied by the concentration of C7H5O2 minus all over the concentration of the benzoic acid, which is HC7H5O2. Now we just plug in our equilibrium expressions here. So 6.5 times 10 to the negative 5 is going to be equal to x multiplied by 0.150 plus x divided by 0.050 minus x. And so at this point we can do the x is too small approximation. And then we'll check the validity of that. So get rid of x here and x there. And so then we just divide these two and then divide our result on both sides, and we'll find x. And when we do that, we get x is equal to, x is going to be equal to 2.2 times 10 to the negative 5. So 2.2 times 10 to the negative 5. And again, if we divide this by the original amount, which is here, we'll divide 0.050, multiply that by 100, and we get a percentage of, let's see, where's the percentage? 0.044%. So 0.044%. So definitely less than 5%. So that's it validates the use of the x is too small approximation. And now to find the pH, since x is this is x is the hydronium ion. So all we have to do is take the negative log of 2.2 times 10 to the negative 5. And when we do that, we get 4.66. So the pH is equal to 4.66. Okay, so that's using the equilibrium method. Now let's try the Henderson-Hasselbach equation. And so the Henderson-Hasselbach equation is, so if we put our work down here, the pH is equal to the pKa plus the log of the base over the acid. So the log of the concentration of the base over the concentration of the acid. So if we have the Ka value, we need to take the negative log of the Ka. If we take the negative log of the Ka, we get 4.187. So the pKa is equal to 4.187. 4.187. 8 is the last sig fig, but we're keeping 1 to avoid rounding mistakes. And the concentration of the base is here. This is the concentration of the base. This is the concentration of the acid. So we just plug all of that in. So then the pH is equal to 4.187 plus the log of the base, which is here. So it's going to be 0.150 over the concentration of the acid. So that's 0.050. And so we take the log of that, and we're going to get 0.477. So then this is equal to 4.187 plus, what did I say? 0.477. 0.477 with the line under there, so we only can go up to there for our sig figs. And when we add that together, we get 4.66. So we get the same answer. We get the same answer for both the equilibrium method and the Henderson-Hasselbach equation. Now we could check our approximation here. Is the answer for this within reason? Can we? Does it follow the 5% rule? Right. So what we can do then is we take the 4.66, and we find the H plus concentration by using this equation. So the H3O plus concentration is equal to 10 to the negative pH. So we take when we take the negative 4.66, put that into the equation here, and then raise it to the 10 power. If we get that, then we get 2.2 times 10 to the negative 5. So then we get 2.2 times 10 to the negative 5, which is what we got before, and we already checked it, and we got 0.44%. So that you could do the same thing with the Henderson-Hasselbach equation. So I hope this was helpful. Again, you could do either the way of using the equilibrium in your ice chart, or you can plug everything into the Henderson-Hasselbach equation, and you can check the 5% rule for both. If you like this video, if you like my videos, please like, share, subscribe, hit the notification bell, and put a comment in the comment section. Let me know what you think. Thanks for joining me, and I'll see you next time.